today's video lesson, I wanted to go over an implementation of a hash function. So in the previous lesson, you learned how to do this on paper, and we're going to connect the two. We're going to show you how to do it on paper and how that connects to what that looks like in code. So to mildly review, a hash function is a mathematical function that takes an input and produces a fixed output. It is deterministic. It's used to map data of any size to a fixed value size, and it's usually used to retrieve data. I don't know if you can see. Let me see if I can close up on the image. And I can a little bit. So this is an image from your book. It says address calculator here. This is going to be what the hash function is. So the hash function is kind of like an address calculator. So we are given a key, we place this to the hash function, and then we get a placement in the table. So that's what that looks like. And that's in your book. And we also have the issue of collisions when two hash keys index to the same, when two keys hash to the same index in the hash table. Okay, so we're going to look at the next slide. So this is a hash function in C++. Traditionally, you're going to see size underscore t as the type for the hash function, because we're not going to use the int type. We're not going to be having typically negative numbers, but we do need something that's signed and unsigned. So we're going to use size t. So you're going to see this. And we have a hash function that takes in a string or a key, and there's something unusual here. So you might be wondering to yourself, how can a key or how can a string be a constant? So this is something a little bit different. When you use constant like this, it sends a message that you need to make sure that this string is immutable. So that's a special use case. So I'm sorry if that's confusing, but that's just how it is. And for character C in key, so this is a really cool way to iterate through a list using this colon. It's similar to how you would iterate in Python. So you would read this for character C in key. So for each character in the string, we perform the hash function. And the hash function is we take the value, we leftwise bit shift 5, add the hash value, and add the ASCII value for the character. And then you return this value modded by the size of the table. And so you take this hash function and you keep doing it until you finish the string, and then you mod this value by 10 to get the index that we're going to be placing this value at. And so let's go down here. There's an example that I have. So it starts as empty. So you're going to notice that everything starts as empty. And we're going to be given a hash function called Atlas. Let me go to the code so you can see that. So that's over here. So Alice with a score of 95. So it starts out as empty. The hash function is called. It takes the parameter Alice and a score. And when the function is complete, when we do that leftwise bit shift times 5, I can't remember immediately. I can't remember. Yeah, hash value bitwise 5 plus the hash value plus the ASCII. So after we do that and we finish that and we modded it by the table size, we get a 3. So that means that Alice's value gets saved into index 3 of the hash table. Then we have a situation where we're going to collide. So in the next example, we have Bob, who also gives a value of 3 when the hash function is complete. So, collision. So the index, so the linear probing algorithm is run, and it also uses size t hash table linear probe. So while the index is occupied, you're going to move on to the next one. You're going to check the next index to see if it's taken up. And if it's not taken up, then we can use that index. So we're going to return that index. So in this example, with hash function bob equals 3, we take the index plus 1 modded by the table size, and that gives us the next value, and that's 4. And so, okay, this is Alice at 3, so that means we can place Bob at 4. And then we do this again with Charlie, and we get another collision. So the same thing goes. It's no problem. You just do the same, you just do the linear probing, and then it takes you to the next one. So in this case, Charlie is going to be at 5. So in closing, your book, let me zoom out really quick, because it's zooming in too much and you won't be able to see the whole slide. So your book says that a hash function tells you where to place an item in an array called a hash table. So the thing that I want you to remember about hash functions is that they're deterministic. They're mathematical functions. They take an input and produce a fixed size output. This is referred to as a hash code. So the key points are, again, deterministic, fixed output size, it's efficient, it has uniform distribution. So it uniformly distributes across the space to minimize collisions. And it's a type of collision resistance. So collisions are possible, but a good hash function minimizes the likelihood of the collision, especially for different inputs. So that's your hash function. Also, they're used in cryptography and databases. So I put a note here at the bottom. The concept of hash functions and hash tables is a fundamental topic that often appears in database courses. I actually had this. We went over this in the databases course at Cal State Fullerton, and wherever you go, you're probably going to go over this again too. What I want you to remember about linear programming and linear probing is it's a collision resolution technique, and you use it in hash tables. When a collision occurs, linear probing gets the next available slot by linearly traversing the table until it finds a spot that's empty. And then, so that's covered in the example. That's pretty much it. So I'm going to enclose the code so you can take a look at that. And if you have any questions, just let me know. Thank you so much for listening and have a wonderful day.